In addition then to specifying measures of central tendency, we want to talk about measures of dispersion. Okay, the simplest one to compute is range. I don't need to write anything in there. What's your high score? What's the low score? Take the difference between them. All right, that's one of the simplest things we can do. Very often we see that variance is measured. And so what is variance and how do we compute that? And so when we compute variance here, the units the data are measured in, so if you're measuring, units are the squared units. Of the data. Okay, we can talk about population variance and we can talk about sample variance. For population variance, we use lowercase sigma squared to denote population variance. To compute this, this is given by the summation from I equals 1 to capital N of the quantity y sub I minus population mean mu, close the quantity and square it. So that says we square all these differences and then add up, divide by population size capital N. For our sample, the sample statistic is given by lowercase s squared. The formula looks similar to what we're looking at for population. That is, it's going to be the sum from I equals 1 to lowercase n of the score yi minus the sample mean y bar, close the quantity, and it's squared. This entire quantity is divided by the sample size lowercase n minus 1, a little bit different than the population. So if you looked at this and said the biggest question that comes up is why minus 1 when over here I didn't do that. Okay? The reason is that for a population, if we know the population, there is one and only one value sigma squared, right? For the sample, we can draw perhaps infinitely many samples or a lot of samples that are different from that population. And so say for instance, just in this room alone, we all sample the same population. We all have different samples. We all compute our own s squared value. Okay? And so we could take all these possible s squared values, and the idea is that if we looked at the average of all those s squareds, they should be sigma squared, right? That's what's supposed to happen. And the only way that happens, though, is whenever I use little n minus 1 in this denominator. So that must, when we do that, we refer to this s squared value then as an unbiased estimate of sigma squared. Okay, if I use lowercase n down here, I don't get the idea of the averages of all the s squareds being sigma squared. Okay, so this is an unbiased estimator of sigma squared. Okay, now notice in either case here, the values yi minus mu and the values yi minus y bar, those differences can be either positive or negative, right? In fact, they have to be some positive and some negative if the mean is the algebraic center of the data, right? Because if it's the algebraic center of the data, say that y bar, that means you're going to have some values over here, some values over here, and you're measuring the difference in between those, right? So we're taking each of those differences, negative and positive, and we're squaring everything so everything's positive before we add it up. Okay? So the sum of all these squared differences, so the result of that is that variance is always non-negative. Now wait a second. Why didn't she just say positive? Is variance always positive? So if it's non-negative, I'm allowing for what? 0 and positive. Can I have 0 variance? Well, I must. You put that with an exclamation point. All right. How can I get 0 variance? So suppose you have a sample and all your data are exactly the same. Okay, y minus y bar is 0 for everything. That's how you get 0 variance. Okay, So it's not likely that the population variance is going to be 0, but for samples it's easy to see how that could happen. All right. We can also talk about some computational formulas if we're going to do some stuff by hand. We do a little bit of that in this course. So if you have a sample of size 100, then you have to compute the sample mean, and you have to compute all these 100 deviations, square them, and divide by 99. Okay, so there's a lot of different deviations you have to compute here. There are some things we can do to shorten up our work. So in terms of sigma squared, over here, this numerator can be simplified on for both of these, and so that you can take the sum from I equals 1 to capital N of the yi's squared. Right, without parenthesis here, this means you're squaring the y's first, then adding up. Okay, sometime, let me write the next term. Not to be confused with the sum of the yi's, add everything up, and then square it. Okay, so this one is divided by capital N over here. This entire thing divided by capital N minus 1. Pardon me, no minus 1. Getting ahead of myself thinking about the sample stuff. There, get my whiteout pen warmed up on this Monday morning. I can't cross out with the marker, it just gets a bigger smudge. So that's the best I can do to erase. Okay, we can do a similar thing then for s squared. And that would be taking the sum of the squared yi's from I equals 1 to lowercase n minus the sum of the yi's, quantity squared, divided by lowercase n. Now I can divide by an n minus 1, where it'd be lowercase n minus 1. Now, if you need to help remind you that you square things first, then add up, you could put a parenthesis around like this, if that helps you. It's not necessary in terms of the algebraic notation or the symbols, but again, once we move from this formula to computational formulas, if you don't get this first one right, you can get negative variance. And what do we know? Variance is always non-negative. Okay? So therefore, when you get done computing your variance, it doesn't satisfy the common sense check that it's a non-negative number. Okay? I could have written it over here too. Ran out of space, but I'll write it over here for the s squared. The other thing you could do is take the sum of the squared yi's minus lowercase n times y bar. Only the y bar is squared. And then the denominator is still lowercase n minus 1. Now I've done a couple of things here notationally that you will see me do later in the course, as well as in the textbook and other references. Okay, that summation notation, initially I was really careful here. I equals 1 to lowercase n. Down here I just wrote 1 to n. That's an equivalent notation. So that the I equals, if there's only one index there, you can just write it this way. Also, if there's only one index, or if you just mean to add everything up, notice there's no index up here, the sum of the yi's. Okay, all those are equivalent notations. Okay, it wasn't just that I got lazy. Okay, but you can see all of those. So if we just saying, well, we know the sum of the y's is this. Okay, so that it may be reported just looking like this with no index on it. If it's index specific or needs to be, then by all means we'd use the index, right? Here there's only one y and we're adding everything up, so I don't need to, so I can get away with less specific notation. Okay, these computational formulas then are really applicable in most cases for what we're doing to samples. We'll do one illustration where we talk about a population, but most usually we're looking at samples. So variance, one of the difficulties in working with variance, as I started out here saying, is that the units are the squared units of the data. So if you measure something in meters, variance is in square meters. Okay? If you measure it in grams, then the variance is squared grams. Dollars is squared dollars. So what's a square dollar? Okay? So standard deviation is oftentimes reported instead because it's in the same units as the data you've measured. All right? And so when we measure standard deviation for the population, the notation for a population standard deviation is sigma with no superscript. And so that just means that we're going to take the positive square root of the population variance. And for a sample standard deviation is given by lowercase s, which is the positive square root of s squared computed by any one of the above three formulas. Okay, and so the advantage then to standard deviation is that standard deviation has the same unit definition as the data. Now in our formulas for variance, we saw the score minus y bar, and that's just called a deviation. All right, and so if we're interested in say, well, if all you want is something that's in the same units as the data, then why square everything? Okay, that idea behind the data being the algebraic center means that if I take all those deviations, notice they're not being squared. If I just add up all those deviations for a sample, I get 0. That's the algebraic center of the data, right? So here we recall that y bar is the algebraic center of the data. All right, these deviations here, they could be negative, positive, or 0. Okay, so let's consider the first definition of variance, this one right here. Okay, I need to know the mean, the sample mean, and then the deviation, and then the squared deviations. So if you wanted to work through a formula like this for a reasonable sample size here of 5, okay, if you take and compute all of these into the sum, so the sum of the yi's, if you have a calculator, do you want to get out and check things? So the 10 plus 17 plus 13 plus 11 plus 18, if you add those up, I have 69. The sample size here is 5. So the value then for y bar is going to be 69 divided by 5. $13.8. Oh, not there, it's too bright. Okay, this is an old calculator, so just a note about calculators. It's 20 years old at least, okay, but it's got big numbers, okay, so it projects well. My graphing calculator does not project so well, okay, so If I put a calculator on screen, it's probably going to be this one, just as we work through things. Okay. So if I know what the mean is, the 13.8, then if I compute the deviations for everything here, so I would take 10 minus 13.8, so the first deviation would be negative 3.8. 17 minus 13.8 is positive 3.2. 13 minus 3.8 is negative 0.8. 11 minus 3.8 is negative 0.28. Pardon me, 2.8. Misspoke there. 18 minus 13.8 is 4.2. Now, as a check, if you add these up, you should get 0. So our check here is that we should get a 0 if we add things. Now then, if we take each of these deviations and square them, so negative 3.8 squared is going to be positive, and when I square that, I get 14.44. 3.2 squared is 10.24. Negative 0.8 squared is positive 0.64. Negative 2.8 squared is positive 7.84. Positive 4.2 squared is 17.64. So if we add these guys up, what we're computing is the sum of the yi minus y bar squared. And that sum is equal to what? I have 50.8. Do you agree? All right, so if I want to compute the sample variance, I would have 50.8 divided by what? Sample size is 5. It's sample variance, so I'm dividing by 4. Sample size minus 1. So my sample variance is 12.7 squared units. I don't know what the units were here. And the sample standard deviation would be S, would be the positive square root of this 12.7. .5637. And just to emphasize here, whatever the units are, not squared. All right, a note about calculators. I get asked by email and then during the first class or after the first class, what kind of calculator do I have to have? You know, I don't make any brand recommendations on calculators because whatever's going to serve you well after this course. And so someone in business is going to need a different calculator than someone in a science area. All right, so statistically what you're wanting to look for, and I think I addressed this in the syllabus, is you want a calculator that at a minimum will do univariate statistics or single variable statistics. And so that means it will compute means, standard deviation, and variance, okay, for one variable at a time, okay. Some of those you can see on calculator models that are less than $20, okay. If that, you need more than a checkbook calculator, all right, that add, subtract, divide, multiply. You need more than that, okay. But if you can get univariate statistics, bivariate statistics, those calculators, some of them are more affordable than others, but if you can start getting into graphing calculators, there's a lot of tools there, but some of them you may not use in your particular discipline. So that's why I don't make a recommendation for a specific brand of calculator, okay? Because I don't want to recommend something to you that's not going to be useful to you later. All right, univariate statistics or single variable statistics at a minimum is what you want to look for, and those are very affordable. If you see some that have bivariate statistics, and so by bivariate, later on in the course we'll talk about doing line of best fit or regression analysis or correlations, and so they would be able to handle that as well. Okay, but so now whatever calculator you have, if it does that, or whatever one you're going to get, keep the owner's manual. Okay, learn how to do the stat functions on your calculator. Okay, every calculator is different, and so how those functions work, so I can't possibly know how all those work, so you need to take time to learn the stat functions on your calculator. So before the course is over, that may be to your advantage, say on a test, if it's got some stat functions. Now there's some limit to that, and I'll explain as we go along what my expectations are as far as what I expect you to do and what I expect the calculator to do and what kinds of things you show on the test. Okay? All right, kinds of calculators, and they're very, very different, and I always have to look up how to do it on one of them. So anyway, so that's my spiel about calculators. All right? But, I mean, the reality is, you're either going to, in practice, you're going to be collecting data, and if it's a small data set, you may be doing things on your calculator, or you're going to be using software. We're not going to be doing things like this. This is in practice. In practice, we're going to be very this century, okay? As we go through things, though, to learn it and understand what the formulas are and how to do those, we're doing some things by hand, okay? But in practice, we're going to rely on calculators and software, and so we're going to get to that point. Okay, we're not going to do this all summer. Trust me. Okay. That said, we're going to do this another way. All right. I talked to you about the computational formulas. So the problem with the deviation formula that we see here is that we have all of our data. We have to compute all the deviations and then square all the deviations. So far we have 2 times n opportunities to make a mistake. Right? I don't need that. Okay, so I want to try and minimize that. That's what the computational formulas do. All right, so here are our yi's, and if we compute that, we already know the sum of our yi's from the previous page is equal to 69. The sum of the squared yi's, well, now we still have capital N opportunities, or pardon me, lowercase n opportunities to make a mistake, but it's less than before. 10 squared is 100, 17 squared is 289, 13 squared is 169, 11 squared is 121, 18 squared is 324. And so if we add those up, the summary statistic we have then is the sum of the squared yi's. Okay, so if you add all of those up, I come up with 1003. Do you agree? Okay, hearing no votes to the contrary. Loudest vote wins, and I guess that tends to be me right now. All right, s squared then is computed by taking the sum of the squared observations. So go back to that computational formula. Over here on the right, if we look at this top one, the sum of the squared yi's. Here, so sum of the squared yi's is 1003 minus the sum of the yi's, which is 69, and only the 69 is squared. The sample size 5 is not, divided by sample size minus 1, and so if you compute this, and I got the 50.8 over 4 again. Well, that's good. the other way we could have done this is using this next formula here, which we need the sum of the squared yi's and y bar and down here again. All right, so if we do this formula here, we end up with 1003 minus sample size is 5. The mean we figured on the previous page was 13.8. Only the mean is squared, and we divide by 4. And if you go through all this, again, you come up with 12.7. Now, if you're going to do these formulas, the places where rounding errors can occur is here we came out to 13.8 at that single decimal place. If it goes out several decimal places and you round, using this last one here, if you've rounded them off the mean, that rounding error is going to affect your answer here. Okay. If you, up here, we hadn't rounded anything. All right, because my data were also whole numbers. And we were dividing by 4, so everything there was kept us at a manageable number of decimal places. All right, so any one of these 3 ways of doing it is fine. So the 3 ways again being, we could have used the squared deviations approach. Okay, here just using the 2 sums, or we could have used this sum of the data squared and then the y bar formula. Okay, so any one of those is okay. What you might expect from me is that if I give you summary statistics, I may give you the sum of the y's, the sum of the squared y's, okay, and then go from there, or sum of the squared y's and y bar. All right, what do I give you, and what then work from there, okay? That's most likely what would happen on the first test, okay? Rather than asking you to do stat functions on your calculator from the first test. That'll come later. Okay. All right. The next measure of dispersion is the standard deviation of the mean. We illustrated this concept really with variance earlier, but again, suppose each of us takes a sample of the same size, lowercase n, from a population. We each have different samples. We each have different data. The only thing we have in common is that it's the same sample size, lowercase n, and it's from the same population. So we're trying to get to the same values. Our sample statistics are going to be different because our samples are different. Okay. Now, if each one of us computes a y bar, all of our y bars, the idea is we're trying to get a handle on what is the population mean mu. And so we expect our y bars to be close to the value of mu, right? That's why we're drawing the samples, is so we can get some information about the population, draw some inference about the population. All right, so we each have different data sets, we each have different y bars, we each have different s squareds. Okay, so my question then, if my data, I measure, each of us has an s squared for this variance, and we can get the standard deviation of our samples, what's the variability of our collection of y bars? Okay. So how variable is y bar? Because y bar, I can get a whole set of those. If I have an infinite population, I can have infinitely many y bars. And all those y bars then are a data set. Okay? And how variable are they? So what is standard deviation, or what is variance? It's how variable about the mean is the data, right? So when I look at the collection of y bars, I want to say how variable are the y bars about the mean, and the mean is mu, right? Okay, so what would you expect? I'd expect that those y bars tend to lie closer to the value of mu than an individual score does, right? Okay, so if that's what this first sentence means here. Means are less variable than single observations. The collection of all the y bars is going to tend to be more like mu, hence less variable. Okay? So consider the population. So the only values in the population are 3, 0, 1, and 2. capital N is equal to 3. This is the one place where we're going to compute a population variance. Okay? Our population variance is 2/3. How do I know that? Well, our mean here is equal to 1, and I just use the squared deviations formula here. So this is y minus mu quantity squared, y minus mu quantity squared, y minus mu, right? Divided by capital N, which was 3. So that's where the 2/3 came from. Okay, so now if we just consider all the samples of size 2 that we could take. So 0, 0, 0, 1, and then I have a 1, 0 down here, so however they occur in order. All right, so I have, what's the mean of this sample? Well, 0 and 0 has a mean of 0. This sample has a mean of 0.5. This sample, 0 and 2, has a mean of 1. 1 and 0, again, a mean of 0.5. Here I have a y-bar value of 1. A y-bar value over here of 1.5. 1, 1.5, and 2. You agree? So I go through all of this. These are all the possible samples of size 2. So this is the population of all the y-bars, isn't it? All right. So we compute each of the sample means, which was done on the next page too. I guess didn't need to write them all out, but we did. So I want to compute the variance of the population of the y-bars, since these are all the possible y-bars there are. Okay, so what we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 different samples, okay, or 9 possible samples, I guess we say. So capital N here is 9. For this, this is a different population. Capital N of 3 before was for the individual scores. This is the population of y-bars. Okay, so what is the sum of all these y-bars up here? So we can call this is going to be our y1 bar, all the way down to the last one, the 9th y-bar. So now my index, the sum of the y-bars, add all these guys up. The sum of the y-bars is equal to 9. The sum of the squared y-bars So that means I'm going to take 0 squared plus 0.5 squared up through the last ones, 1.5 squared plus 2 squared. When I add all these squared values up, I have 12. So if I want to talk about the variance, of y bar, it's going to be equal to, sum of the squared values is 12 minus the sum of the values is 9 squared divided by capital N, which was 9, divided by capital N, which is 9. So I'm using this computational formula right here. My data are y bars instead of y's. Everybody with me on that? All right. So when I get this, I have all these 9s everywhere. Everything cancels out pretty nicely. I have 3/9. 3/9 simplifies to 1/3. This is a population variance, so I'm going to call it sigma squared, and it's of the y bar, so I'm going to subscript this with y bar since it's not the data. Okay? So this is our notation here, variance of the means. The subscript's the variance of what? So for our initial variance, we didn't have a subscript on it. We could have put a y there. Okay? How does the variance of the y bars compare to the variance of the population of y's? What was the variance of the population of y's? 2/3, right? So sigma squared was 2/3. Sigma squared of the y bars is 1/3. The means are less variable than the data, right? All right, we could also talk about the standard deviation of the y bars, and that would be the positive square root of 1/3, and I'm not going to write that any differently just now. Everybody with me so far? The standard deviation of the mean is also called the standard error of the mean. Typically, we reserve the term standard deviation for raw data, the y's. Whenever you look at the standard deviation of a function of the data, we call it the standard error of whatever the function is. All right. So the mean is a function. So standard error refers to the raw data. Pardon me. Standard deviation refers to the raw data. Standard error of the mean means we've taken a function of the data and we've computed that standard deviation. Okay. So in general, we can always say that the standard error of the mean is smaller than the standard deviation of the population from which the sample is drawn. And we demonstrated that here with our sample of size 2. Okay. For population, how do we write this in general? So sigma squared y bar is equal to the population variance divided by the sample size. So that's why we divided that 2/3 by 2. That's where the 1/3 comes from. Okay. Sigma y bar is equal to lowercase sigma over the square root of n. Okay. This is my shorthand here at standard error of the mean. Now for our samples, all right, we are going to write this as lowercase s with subscript y bar and it's squared. All right, this is equal to the sample variance s squared divided by sample size lowercase n. This estimates sigma squared y bar. On screen. Okay, when we take the sample, we don't know what sigma is, right? So therefore we have to use our sample information, and so this s squared with subscript y bar estimates the variance of the y bars. And if we take the standard deviation or of the y bars, or the positive square root of this, we end up with s with subscript y bar is equal to lowercase s over the square root of n. This is referred to as our estimated standard error. Of the mean, or estimated standard error of y bar. All right. Now in practice, we don't know the population. If we knew the population, we'd be done. All right. We don't know the population, and so whenever in practice we're talking about the sample, and so what tends to happen then with our language is that when we talk about what's the standard error of the mean, we're actually talking about this piece over here. We tend to drop that estimated and say what's the standard error of the mean and just use the sample information because we know we don't have the population. Okay, so I guess that one's probably laziness. All right, but so that when you read this, read things, most likely that's going to say what's the standard error and you have to know that's based on sample. Okay. Why this becomes important then is if we know how variable the means are, then we can start making some inference about the population mean, and we'll use that. We'll use the standard error information coming up then in some of the decision-making tests that we will learn in a few lectures. Coefficient of variation, also just referred to as CV. I only see this in terms of sample data. Okay, it is a relative measure of dispersion. Okay, it is meaningful for ratio scale data only. Ratio scale, remember, has that absolute 0. Ratio scale means that whenever I talk about things being 10 units versus 20 units, I know 20 is twice as much as the 10 because of the ratio scale. Okay. It allows for the dispersion of random variables to be compared when units of measurement from one variable to the next may not be the same. All right. How we compute CV. What that means by relative measure of dispersion is it takes the measure of dispersion sample standard deviation and divides it by sample mean y bar. All right, so it's units divided by units. So CV is a unitless measure, and it's usually reported as a percent. So we'll multiply by 100%. All right, we note here that some research areas place restrictions on how large the CV can be. For instance, then in reporting the information from a study, and if you report that your coefficient of variation was 22%, the agency you're working for, funding agency or whatever the sponsor is, says, wow, you just didn't do a very good job of controlling data at all. Okay, CV values, you want CV to be low. Okay, and so if you have data that has a high amount of variability in it, then it's less reliable, I guess, in this study. And so that you're taking standard deviation divided by the sample mean. If that's too large, okay, that means you have too much variability in the data. And so we'll talk about things as we move through the course. Then, are there ways we can control that variability? Okay. And so I have seen some recommendations where CV values only report this. Your study's only valid if your CV is 10% or less. Okay, I've seen some that are pretty large. Okay, but the idea that allows different units to be measured. So suppose you're measuring something that's a measure of volume is your unit, okay, and then how do you compare the variability in volume compared to distance? Well, I can't. They're different units, but if I look at coefficient of variation, now they're unitless measures, and I have these two percentages, and I can talk about variability between these two different types of measures when they have different units. That's what that last bulleted item means, okay, is that CV removes the units from that, so that means then now something that's measured volumetrically versus something that's measured linearly or distance, that comparison or that, those judgments can be made reasonably now. Okay, percentile. I hadn't really thought about, I've always taught percentiles, but I guess I just always taught them they were percentiles. And so they are, in fact, some measure of dispersion. It talks about knowing percentiles, where a 95th percentile is, say, versus a 25th percentile. That lets you know how spread out things are as well, okay, or how dispersed data are. So if we talk about the pth percentile, what the definition of percentile is, the value for which at most that p% of the ordered population is less, and 100 minus the p% is greater. And so when we talk about 95th percentile, let's say, so we have all of our data on this number line, and we mark a 95th percentile. Okay, and so what that means is when the data are in order, that means 5% of the data is above this score, and 95% is below. Okay, and so an example, whenever you look at growth charts for children, okay, that you want to know if your child's on a normal growth curve or not. Okay, I always like it whenever the nurse's aide tries to explain that to me, what the percentile is. So they don't always get it right. Okay, what else can we talk about? Maybe a too painful memory for you, your GRE score. Okay, we'll look at GRE scores. Hopefully there's nobody down here. Okay, let's see, suppose up to 800. I was looking at some data once recently and came up with these values for, I don't remember for what year it was. That changes each year. But in this, so your verbal GRE score can be between 0 and 800. 400's halfway. Okay? And so when I was looking at these verbal scores, get on the right one here. .380 was the 25th percentile. So that means 25% were below this score, 75% were above, even though it's not 25% of the distance. That tends to be how they wanted to explain that to me on the growth curve. All right. Wrote very small here. 470 was the 50th percentile. Well, the 50th percentile would be the median, wouldn't it? Half the data is above, half is below. Okay, so it's not the midway point either. It's not 400. Okay, and then I had 550, even closer to that, was the 75th. All right, so the idea of trying is that 25% of the data is in this interval of 90. Another 25% of the data is in this interval of 80. And so it's not uniformly spread across that interval 0 to 800. And it makes sense that it shouldn't be, right? You don't want a lot of grad applicants down here, okay? And I think I had that 400 was actually the 31st percentile on that. And 86th percentile was like 610. Okay. And then one of the others was on quantitative. Halfway point, we think. A value of 600 was the 46th percentile. That means on the quantitative questions that what we're looking at, nearly half of the observations are in that upper 200, right? Very compact in there. And then I had a 730 score. Was the 75th percentile. Someone did get an 800, and that 800 was actually 92nd percentile. How's that happen? 92% are below 800. It means what? 800 is the biggest you can be, so that 8% are getting perfect scores. Anyway, so you get some feel for how dispersed the data are, as well as where it's at when you look at percentile. Okay. Now, some textbooks get into a lot of formulas and stuff about how do you compute percentiles, and I'm not worried about that. Okay, so in terms of if you have a list of data, which ones, if you can get specific ones, those being the quartiles, where you could pretty much divide things up by 4. Good. Median, first of all, quartiles to divide the data into fourths. The first quartile is Q1, or the 25th percentile. The second quartile is Q2, or the 50th percentile. Q2 is also the median. The third quartile then is denoted by Q3, or 75th percentile. Interquartile range is the difference between the third and the first. That is what in the interquartile range says that 50% of the data falls within this distance. Okay, and that's used in the construction of box plots, which we'll talk about in the graphics part, or the graphics lecture. Okay, so back over here, the things that were different here, I marked this as 25th. That would be Q1. The 50th would be Q2, or the median. We called that M sub Y. We also had 550 was the 75th. That would be Q3. Okay. Now, the one thing I wasn't able to get from that would be range, because we don't have what the high and the low scores are. I guess on the quantitative, we know there would be some 800s for high, but I don't know what the low score is. That wasn't released, I guess, in the report that I was looking at. Okay, so how you compare with others then, it says other people taking this test, so many, what percent are above you, what percent are below you.